ladies and gentlemen. And now we are in chapter 4, demand. And last week, not the week before last, we have already derived, or I have already introduced how to derive a demand curve using the indifference curve analysis approach. So, given this, you must be somewhat familiar with this diagram. We have budget constraint, say IA, income budget constraint, and IB and IC. So the change in which variable do we have? Which variable has changed in this case? Is P1, right? So if the budget constraint looks like this, P1 Q1 plus P2 Q2 equals Y. Y is income. So the change in P1 looks like this. And this would be the change in P2, right? And the change in Y. So in the last two cases, P1 remain constant and P1 remain constant, right? Alright, let's have a look, or let's just review how we derive the demand curve. So, what do you think if initially the budget constraint is IA, then the optimal solution for, in this case, would be Q1A, right? This would be Q1A. And the corresponding price is denoted by P1A. So now we rotate the budget constraint from IA to IB. So what happened to P1? Do you think does P1 increase or decrease? It goes up or goes down from IA to IB? The answer should be clear to you. Goes up, right? Because you see your budget set shrinks, right? The budget set becomes smaller. So it must be, in this case, P1 must be goes up. P1 must goes up. So in this case, the optimal solution or the optimal choice for Q1, no, we denote it by Q1B. And the corresponding price should be higher than P1A or be lower than P1A. Should be higher, right? So this would be the corresponding point on the demand curve, right? Because P1 goes up, right? So P1, now this would be P1B, okay? And on the contrary, sorry. So IC, the price for P1 must be lower on IC, right? So in this case, P1 decreases. The price of good one just dropped. So drop from P1A to P1C, and the corresponding optimal choice for Q1 would be Q1C, right? So this is how we derive the demand curve for Q1. this would be the demand for Q1. And in this case, P2 is hold constant and Y is hold constant. And we code the curve passing through the traces or passing through the tangent points, the optimal solutions. We call it PCC, which would be the abbreviation of price consumption curve. Okay? Price consumption curve. And this would be ICC, which is income consumption curve. Okay? So it's ICC and it's PCC. So in chapter 4, let's have a look at the outline. In this chapter, we're going to talk about how to derive a demand curve and the effects of an increase in income, effects of a price increase, and the cost of living adjustment. So if we hold people's tastes, what do we mean we hold people's tastes? Which means given the indifference curves, okay? So indifference curve, a preference or our taste, if it remains constant, which means the numerous indifference curves for us just remain this type. So if someday we just change our taste, we prefer Q1 to Q2 more. In this case, we love Q1 and love Q2, right? Both of them are goods. The more the better. But if someday they are still the more the better, but we love Q1 more and Q2 less. So the curve will just look like this. The new preference will look like this. Okay? So imagine that if we love Q1 and we love Q2, but now we love Q1 more, so I like to hold Q1, right? So I tend to change my indifference curve in this way. Make the indifference curve steeper. Okay, what does it mean by a steeper indifference curve? MRS, the absolute value of MRS is the slope of an indifference curve, right? So if MRS goes up, what does it mean? MRS means the cost or the maximum amount we are willing to sacrifice to obtain an extra unit of Q1. To get an extra unit of Q1, how much or the maximum amount we like to sacrifice. So if MRS goes up, which means we are willing to sacrifice more. In other words, we love Q1 more, so that we are willing to sacrifice more Q2. Is that true? Does it make sense? Okay? So, given the white indifference curve, the white curves, or the red curve, they are different preferences. They are different tastes. But given a set of indifference curve, we said we just hold people's taste. Assume that the indifference curves are stable, so they remain the same shape, the same type. Okay? And also their income, hold their income and the prices of other goods, which means P2, constant. A change in the price of a good would cause a movement along the demand curve. So when P1 changes, you will see the points, the corresponding points on the demand curve is a type of a movement along this demand curve, right? So it's a point moving along this demand curve. So get the points of this statement, a movement along the demand curve. So we may derive the demand curve using this approach. Okay? In chapter 3, we use calculus to maximize consumer utility subject to a budget constraint, and this amounts to solving for the consumer system demand of commodities. Good. Okay. Okay. All right. So you must remember the Lagrangian function, right? It's a utility Q1, Q2 plus a Lagrange multiplier lambda y minus P1, Q1 minus P2, Q2. Okay, and you must remember that Q1 star is a function of what? Is a function of P1, P2, and Y. Is that right? And not only Q1 star, but also Q2 star and lambda star. So lambda, Q1, and Q2 are endogenous variables, while P1, P2, and Y are exogenous variables. Okay? And now, in the first case, we have already analyzed the effect of the change in P1. And in the second and the week before last, we also talked about the effect of P2 and Y. And, okay, I will not repeat again, but you should remember in these two cases, the demand curve would be a shift type, right? The curves just shift either outwards or inwards. Because in that case, P1 should be held constant. P1 is held constant. So any change caused by the change in P2 or the change in Y, any quantity change caused by P2 or Y would just look like this because P1 is held constant. It is no more a movement along the demand curve. It's a whole curve shift. The entire curve just shift outward or inwards. Okay? So if you do not remember very well, you just do go home and practice to derive from here or from here to the demand curve or from here to the demand curve. I've already done that 2 weeks ago. Okay? So, given a specific utility function, we can find closed form solutions for the demand functions. Yes. And actually we have done this, right? Do you remember the Cope-Douglas? If you remember, when the utility function looks at Q1 to the power of alpha, Q2 to the power of beta, then the expenditure on Q1 to the expenditure on Q2 will be alpha to beta, right? Do you remember that? So P1, Q1 is the expenditure on good 1, which would be this proportion of total income. So the equilibrium will look like this, right? And Q2 star equals beta alpha plus beta y P2. So you will see P1 Q1 star or P2 Q2 star. It will be alpha to beta, right? The proportion of the total expenditure on good 1 and good 2 would be alpha to beta. But in the case on the slide, the power is A and 1 minus A rather than alpha beta. So we just make alpha equals A and beta equals 1 minus A. So let's have a look at this. This would be what? A and A alpha plus beta would be 1, right? So it would be AY over P1. AY over P1. And this would be 1 minus A, and this would be 1. 1 minus AY over P2. 1 minus AY over P2. So the case on the slide is just a special case for this one, right? The setting, the Cope-Douglas utility function setting, alpha, beta, the power of alpha and the power of beta, is a general case. This would be a general case, and A, 1 minus A, is just a special case of the general case. Okay? Is that clear? So do you remember the conclusion here? You should remember we have already derived for 2 or 3 times, right? Okay. Okay, with Cope-Douglas, quantity demanded of each good is a function of only the goods own price and income. So we said Q1 should be a function of P1, P2, and Y, but here we see Q1 is a function of P1 and Y. There's no P2, which means good 1 and good 2 are mutually independent, right? Okay? So it's a property for the Cope-Douglas utility function, but not for all type of utility function. So Cope-Douglas demand curve Q1 star equals AY over P1 would look like this. Okay? Given a and y, given the value of a and y, as P1 increases, Q1 would decrease, right? Q1 would decrease. So it's a negative or inverse relationship between P1 and Q1. Okay? And today, let's have a look at the CES. The so-called CES is constant elasticity of substitution. Constant elasticity of substitution. Okay, some of you may maybe waiting for the midterm exam paper, but you will see them. You will see your paper in the third hour, so the last one. So if you are not interested in what we are talking about here, you may just go out the classroom and walk around and come back by 11. It's fine, I don't care. But it depends, it's up to you. But if you just come sitting there and falling asleep, well, I would suggest you just walking around. Don't waste your time here. All right. I'm going to introduce this type of utility function, CES, constant elasticity of substitution. It would look like U equals Q1 to the power of rho plus Q2 to the power of rho, and the whole term to the power of 1 over rho. Is rho. Alright, same thing. The Lagrangian function Q1 rho, Q2 rho, 1 over rho plus lambda y minus P1 Q1 minus P2 Q2. And the first order condition here, Lagrange lambda is the simplest one. Y minus P1 Q1 minus P2 Q2 equals 0. This is precisely the budget constraint. And Lagrange 1 would be what? Alright. So we have Q1 here, right? And we have another Q1 here. So how to do the first part differentiation? How can we do that? It's a chain rule, right? We differentiate this term first, and then this term. So you will see the power 1 over rho will be dropped down here. And the term in the square parenthesis is just this term. And I will omit the content here because it's just Q1 rho plus Q2 rho, okay? Same thing. The power will be 1 over rho minus 1. Is that clear? And multiplied by, now we are dealing with this term. So it's rho Q1 rho minus 1. Is that right? So this term is the result of differentiating this whole term with respect to Q1. And don't forget this part, minus lambda P1 equals 0. and Lagrange Q2 equals, now we are dealing with Q2. We have Q2 here and Q2 here. So it would be the same. 1 over rho and 1 over rho minus 1, rho Q2, rho minus 1 minus lambda P2. And using these two first order conditions, we just move the negative term to the right and derive them. We just divide the first one by the second. So this will be cancelled, this will be cancelled, then rho will be cancelled. So it would be Q1 to the power of rho minus 1 over Q2 to the power of rho minus 1 equals lambda will be cancelled, P1 over P2. Is that right? Just like here. And we may rearrange this just as Q1 over Q2 equals P1 over P2 and 1 rho over 1, rho minus 1. Okay? So you see we have, okay, define a new variable sigma. So this is defined as a new variable sigma. And so Q1 equals P1 over P2 to the power of sigma multiplied by Q2. And we just replace this back into the Budge constant. So we have Y equals P1, Q1 now would be P1 over P2 sigma Q2 plus P2 Q2. So it would be plus P2 Q2. So we would have the final solution of Q2 star. It will be Y over this term. And you will see what? P1 to the power of 1 times P1 to the power of sigma. So it's 1 plus sigma. And P2 negative sigma plus P2 to the power of 1. Alright? Or we may, let me see, we may do something here. What can we do? We may take this term out by P2 negative sigma, so we have